21 centimeter stuff, and he's there to tell us about measuring the global 21 centimeter stuff.
Great. Thanks a lot. So, as Richard said, I'm going to be talking about measuring the global 21 centimeter signal. And I'm basically going to spend this talk hammering home one message, okay? And to become clearer exactly what I mean, when I actually give the talk, but the basic message is, even though people want to measure a monopole as a function of frequency, you have to have angular resolution. And that's what I want to convince you of. But first, let's sort of step back a bit. My slides will transition. And just sort of talk about the big picture. You know, why is it that we want to do this? Okay? What is it that we're excited about? And of course, the idea of 21 centimeter cosmology is fairly old in astronomy, right? You know, with neutral hydrogen, you've got two spin states. You have the proton and electron aligned or anti-aligned, and the transitions between these two give off or absorb a 21 centimeter photon. Now, of course, what you can then do is use this to map, right? You can say, roughly speaking, there's more 21 centimeter emission or absorption in that direction than over there, so there's more hydrogen there than over there. What's new here, what's new in recent years, as I'm sure you guys have heard a lot here at CITA about, is using this for cosmology. Okay? And in particular, what we want to do is apply this at high redshift. Okay? And what we can do is we can use the CMB with background as a backlight. And depending on the relative temperatures of the CMB and the hydrogen, basically this signal can appear as an absorption or an emission signal. And because we know it's the 21 centimeter line, we know that when this photon was absorbed here, that the transition was a 21 centimeter transition. By measuring observed wavelength, we of course have depth information. Right? We know exactly in 3D space where this hydrogen atom was. Okay. And what's nice about this then, of course, is we can actually make full 3D maps. Here's an example of a simulated 21 centimeter signal done by Andrea Messenger and Steve Forlanetto. This is at redshift 8, which we think is relevant to the epoch of reionization, when the very first galaxies were forming. And so what you're seeing here on this color scale is the dark red is very strong, is where you're seeing very strong 21 centimeter emission. So roughly speaking, say there's more hydrogen in these dark red regions and less in these light red regions where you've got weaker emission. And what these white splotches are basically regions around the first structures, around the first galaxies. So your first galaxies form and spew out a whole bunch of photons, and they reionize the intergalactic medium. And so here what you're seeing is that the neutral hydrogen here has been ionized. You no longer have the 21 centimeter line. And so in our map, this is blank, or in the simulated map, I guess. And because you have full redshift information, right, not only does that use a 3D mapping, ideally this lets us make movies. Right? This means that by viewing this 21 centimeter line at different redshifts, in principle, we can map out how reionization proceeded. Right? So what I'm plotting here is redshift this way, and this direction you can think about as angle of the sky, different parts of the sky that you're observing. So red here is where you have the 21 centimeter emission, and you see the same sort of splotches, except they're black here, mostly neutral hydrogen here. At early times, eventually the first structures reionizing the whole IGN, giving you nothing. And sort of more futuristically, mapping the universe is just a good idea for cosmology, right? In this picture, for instance, I'm showing the, to proportion, the co-moving volume of our observable universe. And here in black is what we had, this sort of thick black line is the cosmic microwave background. Here's red fang here, it's slightly kind of out of date actually, that's roughly speaking where galaxy surveys reach. And this light blue here is, what 21 centimeter cosmology will eventually, sort of maybe decades in the future, or maybe sooner, be able to map out. And with more volume, oh, I'm sorry, time machine is telling me I can't didn't complete my backup, but not home. Sorry. More volume just means more modes, measuring more cosmological modes, and 1 over root n stuff, smaller error bars on cosmological parameters. And even with the first generation of instruments, if they're successful with this dark blue strip, we're probably going to be able to push error bars, with some optimistic assumptions, to fairly low values. So here's the error bars in spatial curvature, for instance, lower, if you include CMB and Planck and stuff like that. Now, that's kind of expensive though. Okay. So to make these large mapping experiments to really map out in detail, the full 3D distribution of hydrogen, you have big interferometer arrays typically. Okay, so for instance, you have the MWA in Western Australia. There you've got 512 antenna tiles, each of which contains 16 dipole antennas. And you can imagine that, if you're taking 512 receiving elements of any sort and correlating all that, that's a lot of correlations. Right? This is a very expensive machine. Cheaper, but still fairly, sophisticated is the paper experiment done by people at Berkeley, among others. We've got LOFAR, another big, expensive instrument in the Netherlands, with some receiving elements dotted across Europe. And then, of course, here with CITA, you're familiar with the GMRT EOR outfit, which Greg is involved in. Now, this is a lot of development and very expensive. So recently what people have wondered is there a cheaper way to do 21 centimeter cosmology? Is there a cheaper way that we can, something that perhaps we can do on a shorter time scale now that can still tell us a lot? And it seems like there is. And so what people have gotten interested in is measuring the angularly averaged signal. So instead of measuring the full 3D distribution of hydrogen, instead of having it as both a function of angle as well as redshift, let's just average over the entire sky. Let's average all 4 pi of the sky, and we can plot the results as a function of redshift, or frequency. Right? So we basically take one of these arrows here, average along this yellow arrow here, and get a number. So we measure the average, spatially average brightness temperature of the 21 centimeter line as a function of redshift, and you get a non-trivial curve with a lot of features that do depend on the physics of reionization. And I'd just like to step through now and talk a little bit about this physics and what sort of processes drive this curve. So the first thing you'll notice about this is that it's both negative and positive. Right? It's negative at high redshifts, and then it becomes positive and goes to 0. Okay? And that's because the 21 centimeter signals can appear either in absorption or emission. And which one it is depends on the relative magnitude of what we call the spin temperature and the CMB temperature. Okay, so the CMB temperature is just your 2.73 kelvins at whatever redshift you're dealing with. And spin temperature is defined here using the Boltzmann factor, with the degeneracy factors here, basically quantifying the relative populations of those hydrogen atoms in the excited hyperfine state versus the ground hyperfine state. And final brightness temperature on the globally averaged 21 centimeter signal depends on the difference here. So if T spin is greater than T gamma, then you see it in emission. Otherwise, you see it in absorption. And so once again, this is because the CMB is the backlight for everything. Now, to understand this, though, to really understand what's going on, we actually need a third temperature. It's actually the processes are an interplay between 3 different temperatures. And that third one's the gas temperature. It's what you would call the temperature of the hydrogen. If I gave you gas in this room in a jar, and I said, what's the temperature? You'd be looking at that gas temperature, the kinetic energy of those atoms. And these guys are coupled, and this is what drives the physics of that curve. For instance, you can imagine that the spin temperature is directly coupled to the CMB, right, just by absorption or emission of 21 centimeter photons. You can also imagine, for instance, that collisions, right, between hydrogen atoms can cause collisional excitations or de-excitations of the hyperfine state. And what drives the process initially is residual electron scattering, residual Compton scattering of electrons. So let me explain that. So, early universe, you've got a plasma, and then you have recombination forms of CMB. And right after recombination, of course, and even now, there are very few residual electrons. Okay, but there are some. Okay, you have some residual electrons. And what can happen is that these residual electrons can Compton scatter off CMB photons. And when that happens, then these electrons can sail along and collide with the hydrogen atom. Okay? And that can couple the collisional temperature, the gas temperature, to the spin temperature. Okay? There's this excitation or de-excitation of the hyperfine spin state. So T gas is coupled to T CMB, T gas is equal to T spin, everything is all equal here. So at high redshift, right after recombination, you have no signal. There's no net absorption or emission of 21 centimeter photons. Now, the universe expands, okay? And what eventually happens is that there are just, the CMB becomes too dilute, too few photons per centimeter cubed to sort of find these residual electrons, which are rare, to Compton scatter off of. However, the collisions between hydrogen atoms maintain the equilibrium between T gas and T spin. So those are still equal. But now T gas, goes scales 1/2 mv squared, and v is like a peculiar velocity going as 1 over a, so T gas goes as 1 over a squared, whereas T CMB goes as 1 over a. So the gas is much cooler than the CMB, which in turn means that T spin is much cooler than the CMB, and you get net absorption. The CMB is pumping energy into the hydrogen atoms. Okay? That's this first feature here. Okay. Now eventually the gas itself, the hydrogen atoms themselves become so dilute that the collisions just aren't able to keep T gas and T spin in equilibrium anymore. Okay. And so if you look at those temperatures we talked about earlier, well, you've lost this link, no more collisions, you've lost this link, no more residual electron Compton scattering, and so all that's left is this link between the spin temperature and the CMB temperature, and so the T gas, T spin and T CMB become equal, and once again you have no signal. Okay, this returns to 0. Now the exciting stuff begins. You form the first stars and galaxies. They spew out Lyman alpha photons. And what can happen then is, well, Lyman alpha photons aren't very transparent to, oops. Yeah, that is the one I want. Aren't very transparent to hydrogen. So, you spew out this Lyman alpha photon, it resonantly scatters off these hydrogen atoms. These photons are now sort of in thermal equilibrium with this gas. And because these transitions can, you can have a situation where a hydrogen atom starts at a ground hyperfine state, absorb a Lyman alpha photon, gets up to an excited electronic state, and it comes back to the excited hyperfine state. So that implicitly couples this process to the 21 centimeter line, the spin temperature. And so this now T gas and T spin are coupled again, and remember all this time the gas is cooling rapidly, much cooler than the CMB, so once again you get absorption, start to trough. Now the first supermassive black holes, first AGNs turn on, spew out X-rays, and they raise the surrounding gas. They raise the temperature of the intergalactic medium. Okay? And so what happens then, that these guys are very hot, and you get the hydrogen in emission. okay, net emission of 21 centimeter. And then eventually, as reionization proceeds, where we essentially get rid of the neutral hydrogen content in the universe, and things, roughly speaking, becomes ionized, and what you have left then is no more neutral hydrogen and no more 21 centimeter line. So this is nice because this was some model, right? Obviously, no one's directly observed this area yet. But what's nice is you can really play around with this model. You can turn off the first AGNs. You can vary the emissivity of Lyman alpha from the first galaxies and so on. And what you see is that the broad features of this curve remain fairly, they exist. Okay? But the details, vary a lot depending on your model parameters and, of course, the model itself, and that's great, right? That's sort of the best case scenario you have for observations, right? There is a feature to look for, and once we've measured that feature, that will tell us something about that model. So that's great. And so people have said, great, let's do this. Okay, here is potentially a cheaper way to probe reionization because this was a globally averaged signal, right, over all spatial angles. And so what I need to do, naively, is to take an antenna, say this, which roughly speaking acts like a dipole antenna. Okay, take a dipole antenna which has a very broad response in the sky. This will now integrate over the sky for me. All right, and then I just take my data and I plot it as a function of frequency, and I should recover that curve. Okay? And people have started doing this. This is this right here is in fact Judd Bowman. This is the EDGES experiment done by Judd Bowman and Alan Rogers, and they sort of target this this last bit, this sort of 100 to 200 megahertz region, hoping to see this sort of decay down here. Now, so that was sort of a long introduction, but that's sort of the vision. Okay? We think that the global 21 centimeter signal, sort of measuring the monopole as a function of frequency, might be an easy, not easy, but a cheaper way to probe the EO wall. But, and there's always a but, there's a problem. There's very strong foreground contamination, right? You go out there with a dipole, like EDGES, and you make this measurement, you are not going to see the curve I sketched out. You are going to see the galaxy. Okay? For instance, our galaxy, we know, has a very strong synchrotron emission, right? And you are going to see that. So, and related to this problem, I think a lot of experiments are non-optimal. Right? An experiment like EDGES, the great effort, and they have a very interesting upper limit. Lower limits on the duration of reionization. But I don't think it's the optimal way to build these experiments. And that's sort of the case I'm going to argue. And what I'm going to argue is that we need to design experiments with better angular sensitivity, despite the fact that we are trying to measure the monopole. Okay. All right, so first let's get a sense for the magnitude of the problem. Okay, like how bad is it? And so to do this, we've got to construct a foreground model because the low frequency sky, so we're sort of targeting here to 30 to 100 megahertz, the low frequency sky is very poorly surveyed in terms of, say, the galaxy. And so one approach is to do a principal component analysis. And this was done by Angelica and Phil Rivera-Costa in 2008. And essentially what they did was, all right, let's take the sky. This is the sky in galactic coordinates. Right? Here's the galactic plane, radio frequencies, and here's the northern polar spur, and you can see some really bright sources like Cassia, for instance. And what they did was they looked at small regions in the sky that were relatively well covered by surveys. Okay? And by that they meant they had at least 11 different surveys at 11 different frequencies from 10 megahertz to 94 gigahertz. And they looked at the spectra in those regions, and they formed a principal component basis set of spectral templates. Okay. And then what they did was they took those templates, those spectra, and expressed the entire sky in terms of these principal components. And so here is sort of is the sky decomposed into the strength of each principal component. And what they found was they could account for 99% of the foreground power in those well-covered regions with just 3 components and nothing more. And for the rest of the sky, if you just took these 3 components and basically extrapolated, you could describe all empirical data to within about 10%. Okay? That's nice, but I have a problem with this. Okay? It's not the 10%. I don't think we're going to improve on that until we get better empirical constraints at these low frequencies. My problem with simply using this for say, a forecasting exercise, when you want to see how well your experiment can do, is that if you're forming a model out of 3 principal components, you're dealing with a 3-dimensional vector space. Okay, this is not the full dimensions of your spectra, if you like. Right? If you have a spectrum that's sampled at 1,000 frequency channels, in principle you have a 1,000-dimensional vector space. And so what the danger here is, you see this a lot in the literature actually, where if you use this model on its own to do forecast, you will find that you will measure 3 modes in your data imperfectly, that's these 3 modes, and all other modes you will measure with infinite signal to noise. So what we did was then we said, all right, well, let's put together an analytic model for the spectra, which is a phenomenological one, the simplest model I can put together that explains all the data. And then we took the first 3 components from their paper, and then we sort of extended it to all higher components to make it fully dimensional. And then we also added some randomly distributed bright point sources, right? Just because the data from which the principal components were formed don't really do a good job capturing those point sources. And so you put this all together, and our model looks kind of like this. It's bad. Okay? This is at 100 megahertz, and if you look at the scales here, the cleanest part of the sky at 100 megahertz is at 200 Kelvin. Okay? The dirtiest part is, about more than 10,000 Kelvin. Here I sort of cut off the color scale to bring out a little more contrast here, but it's severe. And if you imagine averaging over all angles, which is what is relevant for these global signal experiments, if you do that, you get something like this as a function of frequency, between 30 to 100. So you've got typically tens of thousands of Kelvin in these foregrounds. If you compare it to what you're trying to measure, this here, the most prominent feature that we're trying to measure here, between 30 and 100 megahertz, is 0.1 Kelvin. Okay? So you're trying to extract this 0.1 Kelvin dip from beneath this, tens of thousands of Kelvin foreground. Now, so you got to subtract off the foreground somehow, and the usual way of doing this doesn't work very well. Okay? And by the usual way, what I mean is what people want to do with the tomographic mapping experiments. So what people propose for those experiments is, all right, let's look along a single line of sight. Let's look in a certain part of the sky, a certain pixel on the sky. And then what I'm going to do is I'm just going to plot the spectrum. Okay? I'm going to plot my measured values as a function of redshift. Just looking at the spidery structure as well as the sort of Swiss cheese topology we saw before, the cosmological signal you see is very, very jagged. Right? It fluctuates rapidly. The foregrounds we just saw are extremely, extremely smooth. Okay? So that's great, right? So I measure this plus this. All I have to do is subtract out the smooth component, and hopefully what's left is this jagged component. That might work for the mapping experiments. We don't know yet. No one's actually, fully done the mapping experiments. But this is not going to work very well at all for this global signal experiment, right? The signal we're trying to measure is not a jagged curve. This is very, very smooth. It's not quite as smooth as this, but you're trying to take smooth and smoother, and with these differences in amplitude, you're not being able to separate those out. And that's what's limiting experiments like EDGES right now. They're only able to make a measurement where this transition here, well, they only would have been able to make a measurement if this had been basically a step function, a very sharp function, okay, so that they could distinguish between the two. The universe isn't like that. We don't expect abrupt reionization where you have neutral hydrogen and suddenly all the hydrogens ionize. So, you know, because of this, they haven't been able to do any better. And in fact, the problem's worse than this. It's not that this doesn't work well. Rigorously, it doesn't work at all. Okay? Because if you think about taking out the smooth component of a spectrum, what you're really doing, right? What you're really doing, well, one way of doing it is to Fourier transform the spectrum, brutally downweight the really smooth Fourier modes, right? And then Fourier transform back. Now, all of these operations are invertible matrices, right? So the whole process is invertible. So if you take, you know, a vector, your data vector, and you multiply with an invertible matrix, you haven't changed the information content. You just jumbled some numbers around, right? And so if you do something like, you know, a Fisher matrix analysis, or, you know, something more sophisticated, you can do simulations, stuff like that. There's no change in information content. Right? There is going to be no change in the error bars that you assign to your measured cosmological or astrophysical parameters in your model. Okay. And really, what's at fault here is the fact that there's a lack of redundancy. You're trying to measure the spectrum, so you know, if you measure 100 points here, each point is a number, and you have no clue whether that number is foreground or signal or some of both. And what I think, though, is that there's a solution here. The solution here is to have angular resolution in your experiment. The angular resolution provides the necessary redundancy. Okay? So put one way, we're trying to measure this cosmological signal, right? We're trying to measure a monopole as a function of frequency. So spatially, our signal looks like this. The foregrounds look like this. These guys look very, very different. Right? So, in particular, anything that you see, any structure that you see spatially, right? Anything that's not a monopole, you know automatically is a foreground. Moreover, we can start doing clever things. You can say, okay, if I do have the angular resolution, if I can resolve out the galactic plane, then all right, well, in my analysis, let me just downweight the galactic plane massively and have it not be included. And similarly, you know, I could even, you know, say, take two neighboring pixels. Okay. I can difference them. The cosmological signal is exactly the same in those two pixels. So, in the difference, you know, in the difference map, what I have that must be pure foregrounds, and I can feed that back into my analysis to help me.
Is the cosmological signal just a monopole? Because one set line and alpha.
Yeah. So right. That's an excellent question, and it's a matter of scale. So what you'll find when I show the plots later is that I'm asking for very, when I say I need angular resolution, I just mean that I don't want a dipole antenna integrating over the whole sky. But something like 20-degree resolution, for instance, it is more than sufficient. And so, you know, basically, it is roughly a monopole on those large angular scales. You know, we're not talking like, you know, the mapping experiments, which typically have like 4 to 15 arc-minute resolutions. You know, another way to put this is to think about the cosmic microwave background and how we subtracted foregrounds for that. Okay. With the CMB, we're not trying to measure a function of frequency, right? We're trying to measure a function of angle, right? We're trying to measure these anisotropies. And as a function of frequency, this tells me no cosmological information, right? The CMB is a black body. It is the universe's most perfect black body. Which means that if I were to plot this plot on the right-hand side in temperature units, it's a constant. That's great, right? This gives me redundancy. If I'm supposed to measure the same thing at every frequency, then whenever I do not see that, if I ever see some non-trivial spectrum here for the CMB, then I know that what I have is foreground. Okay? So this here is basically the CMB rotated 90 degrees, right? We want a frequency spectrum, so we ought to exploit the angular redundancy. We ought to, despite our goal of measuring the monopole, we ought to build instruments with angular resolution to do this. Okay, now suppose you did. Okay, suppose you go out tomorrow with your pocket money and you build like your brand new telescope that's going to have angular resolution to do this experiment. Okay. How do we actually take advantage of all this to actually make this measurement? So we can start with the measurement equation, okay, where XS here is what we're trying to get at, and this here is our global 21 centimeter signal that we want to see at the end of the day when we're done. Now, so A here is a vertical stack of identity matrices, and this essentially copies this spectrum to every single pixel on the sky. Okay? So AXS is a series of monopole maps at different frequencies. Okay? Then, in a realistic experiment, you add to that a vector of number of pixels times number of frequencies that contains your foregrounds and your noise. Okay? And that's a function of both angle and frequency, of course. And what you get is, of course, your measured values. Again, function of both angle and frequency. So we measure y. It's contaminated by a random vector n, and we would like to get XS. Okay? That's a solved problem. Right? Write down your least squares estimator for the cosmological signal, where here these pointy brackets here, that's our best guess model for the noise and foregrounds. Okay? So we're kind of being Bayesian about this. Okay? We're saying that the mean here is our very best guess for what we think the foregrounds are like, both as a function of angle and frequency. And the covariance, the noise covariance of this noise vector is the uncertainty in our best guess model. So sort of deconstructing this a little. Yeah. So take your data and first of all do a direct subtraction of the very best guess you have for the foregrounds and noise. That's not going to be perfect, and the rest of this formula basically deals with the fact that we don't know our foreground model perfectly. And so what you want to do next is to downweight certain modes that are particularly uncertain. Okay? And that's this an inverse. And if you sort of do this analytically, make some assumptions about what the noise looks like and what the foregrounds look like, and sort of invert this matrix analytically, what you find is that this here is equivalent to taking your best guess subtracted off data and first downweighting by one factor of your foreground model. So what that does is, for instance, if the galactic plane is super bright, then it downweights that so that it doesn't feature very much in your final result. And then not to downweight by another factor of this, which would be what you would normally do if it were simple plain inverse variance weighting. But the optimal thing to do is to downweight by a factor of this map, which is a high-pass filtered version of your foreground template. You can write down the analytic form for what this high-pass filter exactly is. And what you find here is if you compare these two maps, these blobs here roughly correspond to the worst offenders here. So you're sort of taking the really bad parts of the galaxy and just downweighting them extra. Okay? And actually, if you stare at this map carefully, it's actually not quite the downweighting. There are some negative values here, so it's actually doing a little difference in work to try to subtract off some of these sources. Then you average over the sky to get your global signal. And then after that, there's a little process to sort of decorrelate the spectrum to make sure that the numbers you measure at different frequencies are actually independent numbers. Okay, so that's a prescription and a suggestion for how this experiment should be done. You can go ahead and compute this. You can say, all right, let's just figure out what the error bars are going to be like for an experiment designed like this with this sort of data analysis. And we can compute this, although the parameters are somewhat uncertain. Right? These experiments don't exist yet, so we have to kind of explore the parameter space a little. So first, if you vary angular resolution, like this slide here, on the vertical axis here, I have the errors in your measurement of this global spectrum. which is shown with this dashed line here. This is the same curve as before, but I've taken the absolute value so I can put it on a log plot. So this is the big dip, the most prominent feature at 70 megahertz. And so here are the expected errors for different beam sizes, different angular resolutions. And as you expect, the finer your beam, the lower, the better your errors, the more significant your detection of this bump here. Okay? And there are a number of reasons for this. First of all, with a really fat beam, so this is like this guy up here is my original map, sort of convolved with a finite beam size. With a really fat beam, you're sort of taking a lot of the clean regions and you're sort of contaminating them by having the really bad regions leak into them, right? So you can no longer really just say, okay, I'm going to have most of the information come from the clean regions. Have resolved, and you can, whereas with something like this, you can just really downweight the bad regions and preserve the clean regions. This, and also if you have angular resolution, because foregrounds are spatially correlated, you can now begin to take advantage of these correlations. Okay? So ironically, you might say that, okay, I should just design an experiment that just hones in on this coolest part and just stare at that forever. Okay? Turns out that that's pretty good, but it's not the best you can do. It turns out you do actually gain a little bit by going to some of the dirtier regions. Because of the dirtier regions, you can really clearly measure exactly what the foregrounds are like there. And you can then use the fact that these pixels, these dirty pixels, are really correlated with the cleaner ones, with the foregrounds and the cleaner ones. And to use that correlation to your advantage to help you subtract off the foregrounds and the cleaner parts.
Have you checked whether that that conclusion depends on your model having the same sort of foregrounds in the clean regions as the like if you just say, well, maybe the center of the galaxy is very special, and
yeah.
So tweak the model a bit and say the center of the galaxy is very special and it looks very different from my clean region.
Sure.
Do I still win?
So I haven't done an explicit change in that direction, but the models I am using do have that dependence. So for instance, the models do have a built-in, the properties of the foregrounds in the galactic plane are different from the properties of the foregrounds at high galactic latitudes. What I haven't done is to check how robust that is. If I really make it crazily different, whether that makes a difference. Right. Yeah.
So you showed us this formidable matrix equation of
yeah.
So if I have 5-degree beams, I have about 1,000 spots in the sky. And your typical low noise patch this sky is 100,000 or so.
Yeah.
So you're going then at, let's say, 16 megahertz down by a factor of 10,000 in temperature dispersion with 1,000 beams. Can you give us a qualitative sense of how, 1,000 samples gets me by that much?
It actually, that depends a lot. So it's not, if I understand your question correctly, basically how does it sample with, how does it scale with the number of independent samples you have on the sky? And so it actually, it depends on the parameters you put into your model. It's not a simple root n scaling, okay, because here you're not taking.
Because you
right.
have an order of magnitude improvement for every factor of 4 increase in the number of.
Right. So that basically depends strongly on how correlated you assume the foregrounds to be. Because, let me just show you the next plot, in fact, and I think this will make it clearer. If you vary the spatial coherence scale of your foregrounds, or rather, more precisely, of the errors in your foreground model, if you have very coherent foreground errors, you can do very well, okay? Because then you basically understand, there are very few spatial modes you have to remove in order to get a very clean signal. Okay? So it actually scales much better than just what I'm doing.
I guess the thing I would worry about is that, okay, maybe most of this foreground is provided by sources that are pretty coherent.
Mm-hmm.
But what if one part in 100 of the foreground is produced by sources that are very incoherent?
Right. Yeah, so that's actually part of the reason for why we sort of went and took this more Bayesian approach, where the mean of your foreground vector is your best guess model. Okay. So then the covariance here, so the spatial correlation length is really the coherence length of the errors in your model. So for instance, suppose you formed your foreground model out of some other radio survey. Okay? What this coherence is modeling is the fact that that survey itself is going to have some finite beam, and so that's going to be and so that's actually what we're guarding against, the fact that your survey is not perfect. But the fact that we begin by doing a direct subtraction of our best model, that actually guards against the fact that it guards against a lot of foreground assumptions. And that's actually a better way to do it than just doing a purely statistical subtraction. Because you can imagine, suppose our galaxy were atypical, right? You can write down some statistics for how you think a generic galaxy's galactic synchrotron ought to behave. But I don't really care what a typical galaxy looks like in synchrotron. I care about the fact that I live in the Milky Way and that I have a very specific set of foregrounds that I'm dealing with. Which is a really roundabout way of answering the question.
Well.
Let's talk later. Yeah.
I think it's a basic philosophical issue here. You're looking for a very, very tiny signal. There are many other very tiny things that
I agree. It's a scary process, right? I mean, no matter what you do, because your foreground is so much larger than your signal. No matter what you do, at some point you're going to have to difference two big numbers to get a small number. That's essentially, at some point there is going to be a scary step like that.
It's fundamentally an assumption about what scales are present in each of the two pieces.
Yeah. Okay, so I can also vary the spectral coherence here. Right? I can say the foregrounds are very, very smooth, and so perhaps they're roughly a power law, which isn't a crazy assumption, right? Do your standard E&M problem, electrons spiraling around, giving off synchrotron radiation, that's a power law. But real life is complicated, it's not going to be a perfect power law, and so what you can imagine is, with a fiducial value of the spectral index of alpha equals 2.5, suppose there were some variation in that, going from 0.1 all the way up to 2.0, which is pretty big for alpha equals 2.5. What you find is these methods are kind of are relatively robust when it comes to making assumptions about the smoothness of the foregrounds. Okay? And again, this comes down to the fact that you first did a direct subtraction step, and the rest of the subtraction algorithm is to deal with the fact that that direct subtraction may not have been perfect.
So this, how many power laws are in each pixel?
So
Or each resolution?
an infinite number actually. So what I'm doing is I'm taking an infinite population of, basically I'm integrating over a probability distribution of alphas with this sort of spread. Yeah. Okay, you can vary integration time, as you expect. The longer you integrate, the better, but not by much. Okay, and that's because you are dominated by residual foreground error. It's not the sky noise, that's your instrumental noise. That's not really what is limiting you here. Can also vary how much I trust my foreground model. And obviously, the more I trust my models, the better. Sort of as a fiducial model, I'm sort of taking a 1% error in my foreground model, which is perhaps a little crazy for now, but not something that's observationally crazy. Right? At these low frequencies, if you had a foreground survey surveying these low frequencies, a 1% error just corresponds to having a survey that's good to about 10 Kelvin, which is something that can definitely achieve observationally. And so putting this all together, we have a fiducial model here. Our most optimistic model here, it's sort of taking the best assumptions in all those last few plots, that least optimistic model up here. And what we find is, with a broad range of models, you've got a very significant detection of this guy. And in fact, if you do your math right, this pessimistic model is actually also a significant detection. Turns out that the covariance structure here in your measurement is very favorable to you. Because, as an example, one such source of favorability, I guess, is the fact that foregrounds, generically, their errors increase towards lower frequencies. Whereas with a theoretical signal, there's this turnover, this characteristic turnover, and you take advantage of your statistics to really tease that signal out.
And also you're explicitly looking for a roughness, right? And so that automatically correlates your, really it's the difference between neighboring points that you're looking for, right?
If you had, that's right, so if you had a perfectly flat thing, right? You could, All right, so, in summary then, people have recently gotten interested in doing the sky average global 21 centimeter signal measurement. It might be a cheaper way to probe the EOR. The current experiments really integrate over, a really large expanse of the sky automatically. And we think that's the wrong way to do it. Okay? We think that ideally we ought to have, even though ironically we're measuring the monopole, you need the angular resolution to go to deal with your foregrounds. And we think, based on our calculations, that with some reasonable assumptions, that with the right instrument and data analysis technique, we can actually detect this cosmological dip at pretty high significance. It's finally just, stay tuned. This will all be in writing, hopefully next month, finishing up this paper right now. So thank you very much.
Eric? So one thing that can be difficult in practice is to calibrate instrument for such a wide band. And that would look like a monopole, so you get a wiggle in the calibration.
Yeah.
So is there a way you could use the spatial information in the foreground to somehow fit for calibration, maybe? Or is the way to think about this that this work should imply for your calibration?
Yeah. So certainly, if it's just a bandpass calibration, right, that this wouldn't help you, right? Because then you're basically just that is another monopole as a function of frequency. Unless you could explicitly model that. That's right. So I don't have a good answer to that. I think that you would either have to be able to explicitly model it, or just have a very good calibration across your band.
Chris, does polarization of foregrounds help you agree?
Polarization of foregrounds should help you, right? Because the polar, absolutely. Because basically any extra information you have here that's not a pure intensity monopole is extra information you can feed in there as a prior to help you with that.
Why don't you just ask my question?
No, go.
What I'm going to ask, right?
Okay.
So, what in your opinion, for not just doing some fully basic, where you actually explicitly state what your priors are on the same
So what is my opinion?
What's the disadvantage? Why not just do it fully basic and write down some prior to the foreground?
I personally don't think there is anything. I don't think there is much downside to that. There is naively, at a very naive level, there's certainly a computational downside, right? So we can argue about that, but I think naively.
I guess the question is, what you've done essentially, couldn't you actually map that to just a very formalized version? Is there some, prior that you can put on the thing that's computable, that's equivalent to what you've done?
Yes, I think there is. That is actually something I want to do.
Kyo, question?
Yeah, so do your simulations have frequency dependency in them?
They do not.
And how do you expect to smooth sort of like, one over frequency with the effects?
I actually, so it turns out, I don't think it will make a huge difference, okay? As long as, provided that at your coarsest angle, at the very coarsest frequencies, okay, that you are able to resolve the structures you need to resolve. Because it turns out that since because you're always going to be measuring the monopole, you can prove that the detailed shape of your beam actually doesn't matter. Put another way, you're going to be averaging everything together anyway. So as long as you have a sufficiently narrow beam that you can actually use to map out what the structures are, it actually does make a difference.
One last question, anyone? Is there another way of getting back and forth around the top?
Sorry.
Is there another way of constraining the foreground without?
I mean, yes and no. You can imagine, for instance, right, that with the mapping experiment I talked about earlier, okay, but those typically involve interferometers, and that actually, those will yield very, very good foreground maps, but they're not the right experiment for this, because with an interferometer, you typically throw out the autocorrelation. Right? With an interferometer, you typically, you build fairly cheap individual elements, and you don't bother controlling for necessarily possible systematic in your noise with the autocorrelation. You hope that when you cross-correlate different receiving elements, that a lot of that goes away. So, for instance, an interferometer would be a great way to get you information about the foregrounds here, but that wouldn't be the same measurement as this guy, which is the monopole.
Okay, well, let's thank Adrian again.
Thank you.